Hello math friends, welcome back. This is AP Calculus section 2.2 notes. Today we are going to learn the calculus definition of what a limit is. We've tossed this word around a little bit in previous sets of notes when we were talking about the limit as the secant line between P and Q as Q approaches P becomes the tangent line at P. So we've used the language of a limit before, but today we're going to understand the formal definition of a limit. So first of all, in our box here, we have our definition of what a limit is. And it says that if we have some function f of x, as we take our x values closer and closer to a and plug those into our function, the value of our function gets closer and closer to L. So this part right here in our definition is said the limit of f of x as x approaches a equals L. And that just means that as we take our x values closer and closer to the value of a, the value of the function becomes closer and closer to L, whatever L is. So now, when we talk about limits, we always have to talk about the left-hand side and the right-hand side. And this is very important. In order for the limit to exist, the left-hand limit and the right-hand limit must agree. Meaning, if you plug a number in really close to a on the left-hand side and you plug a number really close to a in on the right-hand side of a, they should be converging on the same value. If they're not converging on the same value, then the limit can't exist. And we'll talk about that more later, and as we see some examples of that, that will make some more sense to you. But right now, let's take a look at the three graphs that we have below. So in the first graph, we have a picture of some continuous function. And so this is a situation where when x equals a, the limit as x approaches a from the left side and as x approaches a from the right side, the value of the function is that value L right here, right? They both approach the same, as they both approach a from the left and the right, the value of the function is L. Now, in the second situation, the limit still exists, but here we've got something else going on. I know it's a little bit hard to see in your paper, but we have a hole right there in our function, and the value at a is actually someplace else down here. Now, I want to make it really clear that the value of the function and the limit of the function do not necessarily have to agree in order for the limit to exist. If we plug numbers in on the left side of a, the value of the function is getting closer and closer to L. If we plug numbers in on the right-hand side of a, the value of the function is getting closer and closer to L. It doesn't matter that the value when x is a is not L. What matters is what's happening as we get really, really close to a. So in example B here, picture B, the limit still exists and the limit is still L, despite the fact that the function doesn't equal L when x is a. And then the last example is very similar, except there's still a hole, but there's no closed circle anywhere else. So the graph just doesn't exist when x equals a. And that's okay. The limit still exists because as we plug numbers in on the left side of a and we plug numbers in on the right side of a, both sides of our curve as we get closer to a are approaching that value of L. And there's an explanation here below. In figure A, the function is continuous at a. In figure B, the function is not continuous at x equals a, and in figure C, the function is undefined at x equals a. However, in all three figures, the left-hand limit equals the right-hand limit, so the limit of the function as x approaches a is L. So then we kind of have this further part of our definition down here that the limit of f of x is as x approaches a is equal to L if and only if the limit as x approaches a from the left side is equal to L and the limit as x approaches a from the right side is equal to L. Okay, so I want to really point out that this a negative means from the left, and this as x approaches a positive means from the right side of a. So I want you to note that we can calculate left-hand limits and right-hand limits separately from each other. And in some cases we do. Sometimes they'll just ask us, what is the limit as x approaches a from the left? So then you just look at the left side of whatever a is. Or if they ask you for just the right, you look at just the right side. But if they ask you what is the limit at a, they are expecting you to look at both the left side and the right side to answer whether the limit exists or not. Let's take a look at a first example here, and I think that that will help illustrate what's going on. In our first example, it says for the function f, whose graph is given, state the value of each quantity if it exists. If it does not exist, explain why. All right, so for letter A, we have the limit as x approaches 0 of f of x. Now it doesn't say from the left or the right because there's no plus or minus, so that means that I have to look at as x is approaching 0 from both sides and make sure that they agree before I can determine what the limit is. I'm just going to darken with black my x-axis and my y-axis so that my graph is a little bit easier to read. All right, so as I am approaching x equals 0 from the left, that would be coming this direction right here. And as I'm approaching x equals 0 from the right, that would be that direction right there. So it looks like as x is approaching 0 from both the left and the right, the graph is approaching 3. So the limit does exist, and it is 3. For B, they want us to do the limit as x approaches 3 from the left. So here's x equals 3. Right here, right? That's that line x equals 3. So as x approaches 3 from the left, there's a hole there, that's okay. As x is approaching 3 from the left, the value of the function is approaching positive 4. Then part C asks us, what is the limit as x approaches 3 from the right? All right, so as x is approaching 3 from the right-hand side, the function is approaching a height of 2. Then part D asks us, well, based on the information from parts B and part C, what is the limit as x approaches 3? So now they're asking us to evaluate it from the left and the right at the same time. So this is where we have to say does not exist. And I always use DNE to abbreviate does not exist because the left-hand limit does not equal the right-hand limit. And if those two things don't agree, the limit does not exist. And then finally, letter E, they're asking us, what is f of 3? What is the actual value of the function when x is 3? Well, here's x equals 3, and that closed dot right there is the value of the function. So f of 3 is 3. This is the value of the function when x equals 3. Example 2 says, explain what is meant by the limit as x approaches 3 of f of x equals 7. And then, is it possible for f of 3 to equal 2? Explain. Okay, well, for the first part here, we can just say, based on our definition of what a limit is, this means that as x approaches 3 from both the left side and the right side, the function is approaching 7. When the function is f of x. Okay, so that's what that is meant by, or what is meant by the limit as x approaches 3 of f of x equals 7. As x approaches 3 from both the left side and the right side, the function is approaching a value of 7. But then the second part, is it possible for f of 3 to equal 2? Explain. Well, the answer is yes, it is. Let's take a look at why. A little graphical explanation here would go a long way. So x equals 1, x equals 2, x equals 3 is right here. We could have any function where we have a hole right there when x is 3, and then the actual value of the function is 2. So we could say, yes, f of 3 equals 2 is possible if there is a hole in the function. Right? So this up here could be 7, and the limit could still be 7, but there's a hole there, and the actual value of the function when x equals 3 is 2. In the next part of our notes, we are going to be using our graphing calculators, so please get that out and get ready to use that to go through some problems with that. Recall that our graphing calculators have some nice features. One of the features that we're going to be using today is that table function that we looked at in section 2.1 notes, where we can enter an equation into y equals, and then we can ask it a bunch of x values, and it'll give us the y values. It'll just plug the x's into the function for us and give us the y values in that table feature, which is going to be really nice and really helpful. So for our first example, it says, use a graphing device, both the table and the graph, to determine the limit as x approaches 3 of this function, which is x squared minus 2x minus 3 in the numerator and x minus 3 in the denominator. All right, so first let's make a table. So I've got my x values and I've got my y values. And if my limit is going to be as x approaches 3, then I want to look at numbers that are approaching 3 from the left side and from the right side. So numbers that are a little bit smaller than 3, as well as numbers that are a little bit larger than 3. So smaller than 3, I'd maybe say 2.9, and then 2.95, and then 2.99, okay? And then larger than 3, I'd say 3.01, 3.05, and 3.1. Okay, so now I'm going to do this on my calculator. So I'm going to bring up my graphing calculator. I'm going to go to my y equals, whatever is, there's something there, we want to clear that out, and we want to put in our function, which is x squared minus 2x minus 3. That's the numerator, so we need to parenthesize that whole thing. X squared minus 2x minus 3. Close your parenthesis, then hit divided by, and then we want to parenthesize our denominator as well, which is x minus 3. All right, so I have my function in y1. Now I am going to go to second level table, and I am going to enter in the x values, and you can just enter right on top of the ones that are there. So I'm going to do 2.9, enter, 2.95, enter, 2.99, enter, 3.01, enter, 3.05, enter, and 3.1, enter. And there we go. We have our corresponding y values all figured out for us. So let's take a moment and let's copy those onto the table on our paper. We had 3.9, 3.95, 3.99, 4.01, 4.05, and 4.1. Okay, so here we are approaching 3 from the left, and here we are approaching 3 from the right. And what do you notice about those y values? They seem to be getting from both sides closer and closer to a limit of 4. So let's write that down right here. The limit as x approaches 3 seems to be equal to 4. Okay? So now let's go back to our original problem and let's do a little bit of algebra. we can simplify this with some factoring. So this would be equal to the limit as x approaches 3 of, we can factor our numerator. That's just an easy trinomial. That's going to factor into x minus 3 times x plus 1. In our denominator, we still have that family of x minus 3. Hopefully you remember, because we talked about this already earlier this year, that when we have that same family upstairs and downstairs, that creates a hole in our graph. So this is now going to be equal to the limit as x approaches 3 of x plus 1, which when we plug 3 in, 3 plus 1 is 4. So when we do this algebraically, we also get a limit of 4. The last thing that we want to do, and sorry, let's put a little note here, and let's just say this creates a hole at x equals 3. Okay, but remember, just because there's a hole there doesn't mean that the limit doesn't exist, right? If you were to try to plug in x equals 3, what would happen? Well, you'd get 0 over 0, so we know that that's an issue, right? Let's take a look at the graph of this. Based on the algebra that we just did, we would expect, because the families of x minus 3 cancel out, we would expect that this to just be a graph of x plus 1, which is a y equals mx plus b equation. That's going to be linear. It's going to have a slope of 1 and a y-intercept of 1. So let's take a look at the graph, and then we'll sketch it on our paper after we verify that that is true. And see, we have our linear function as expected with a y-intercept of 1 and a slope of up 1, right 1, up 1, right 1, up 1, right 1. Well, right here where x is 3, we expect that there is a hole in the graph. So there's a couple ways that we can verify this. One thing we could do is we could do that second level calculate, where we ask it a value, and if we enter in x equals 3, we expect that there should be no y value. And that is the case, right? Y is empty because that's telling us there's a hole in the graph right there at x equals 3. And if we want to see the hole a little bit more carefully, we can look at our window and we can adjust our window. If we just look at kind of that window between x is 2 and x is 4, box in our function a little bit, we can do a y minimum of 2 and leave our y maximum at 10. That's fine. And now if we take a look at the graph, there it is. You can see the hole now. There's a little bit of a gap right there where x is 3. Okay? So that's another way that you can prove the math that we've already done is correct. Example 4, same instructions. Use a graphing device, both table and graph, to determine the limit as x approaches 0 of sine x over x. And it says, note that this function is undefined when x equals 0, right? Because if you plugged in 0 for x, sine of 0 is 0 in the numerator, and x is 0 in the denominator, so you would have 0 over 0, which is undefined. Let's take a look at our table again. So we are going to do what we did before. We're going to choose values that are close to but not equal to our a, which in this case is 0, on both the left side and the right side. So on the left side of 0, I might look at negative 0.1, negative 0.01, negative 0.001, getting really close to 0 from the left, but not quite. And then on the right side of 0, I would choose positive 0.001, positive 0.01, and positive 0.1. So let's go back to our calculator. Let's go to our y equals. We'll clear out the old function. We'll enter in the new function, which is sine x. Make sure you close that parenthesis, divided by x. Okay, now we need to make sure that we're in radian mode. I can see right here the word radian, so I know that I'm in radian mode. If you are not in radian mode, you need to go on your calculator to mode right there, and you need to arrow from degree over to radian, highlight radian, and hit enter and change it, because if you're graphing trig, you need to be in radian mode. Okay, so I'm going to go zoom 7, zoom trig, okay, and there's the curve of sine x divided by x, okay. And I can also take a look at my table, which is kind of one of the reasons why I entered the function in. So I'm going to go to second level graph. There's the table key again. I'm going to plug those x values in that I chose. So it's going to be negative 0.1, negative 0.01, negative 0.001. And then on the other side, it's going to be positive 0.001, positive 0.01, and positive 0.1. Okay, let's write those values on our paper for our table. So we have 0.9983, and then we have 1, 1, 1, 1, and 0.9983. Well, we're trying to figure out when x is 0, which is right in there, so it appears that the limit as x approaches 0, both from the left and the right, is equal to 1, right? So we can go ahead and we can take a look at that graph again. And when we take a look at the graph, it certainly looks like right here, as we are approaching 0 from the left, looks like the value of the function is up at 1. As we are approaching 0 from the right, it looks like the value of the function is up at 1. So we can safely say, because our left-hand limit and our right-hand limit agree, that the value of the function is 1, or not the value, the limit of the function as x approaches 0 is 1. The function actually doesn't exist when x equals 0, okay, because it's undefined at that point and we have a hole there. And if you want, again, you can do the same thing that we did in the previous problem. You can zoom in on that spot. But right now, I'm going to go back to my paper. I'm going to sketch a picture of what this graph looks like for future reference. And our graph has a hole right here and looks something like this on either side. Okay, sorry, it's not very even, but that's basically what it looks like. And little note here, we know that x cannot actually equal 0 because this function would be undefined. However, because the left-hand limit and the right-hand limit both agree, we can say that the limit of the function as x approaches 0 is equal to 1. Our last example is our most interesting one. We always save the best for last, right? This function is also defined when x equals 0 because we have the sign of pi divided by 0, which, whatever that is, you can't divide by 0, so that's something undefined. And again, we're looking at where x is 0. So let's start the same way we've been starting with each of our problems. Let's build a table, and our x values, since x is approaching 0 again, we're going to choose the exact same x values as we did in our previous problem. Negative 0.1, negative 0.01, negative 0.001 on the left side, and then positive 0.001, positive 0.01, and positive 0.1 on the right side, knowing that our limit is going to be right in here, so we're kind of hoping that our values, our y values, converge on something there at that point. Let's go ahead back to our calculator and let's put our function into our y equals clear out what we have. And this time, pi divided by x is inside of our sine function. So it's going to be sine of, the pi key is second level above the caret. The pi is right there. So it's going to be second level pi divided by x. Make sure you close your parenthesis. And again, we're already on that Zoom 7, that Zoom trig. Okay, so that's fine. Before we look at the graph, though, let's look at the table. So I'm going to go second level table. Okay, that's weird. I just have a big, long list of zeros right here. So now, this doesn't really make sense because I don't think that the limit is 0 if we can't actually do 0, right? So something goofy has got to be going on here. Let's take a look at the graph and let's see what the graph looks like. So if we graph it, oh, okay, so we've got something crazy going on in here. And if we want, we can zoom in a little bit more and take a look a little bit closer at what's happening here. So maybe I want to go to my window and I want my x-min to be like negative, I'm just going to zoom in close, so negative 0.1, and I'll do my x-max to be positive 0.1, and I'll just turn my x scale off. My y-min and my y-max, since this is a sine function with no amplitude change, positive and negative 1 should be where the graph lives on the y-axis. So I'll just change my y minimum to negative 2 and my y maximum to positive 2. So let's take a look at our graph. Holy cow. So this thing seems to be going crazy the closer you get to 0. All right, and basically our graph is just oscillating between negative 1 and positive 1 on the y-axis, and it never settles on a value because the left-hand side and the right-hand side are not approaching the same thing at the same time. And the more you zoom in, the more this thing oscillates. So if we were going to try to draw it on our paper just to illustrate what's going on, if we were to draw a coordinate plane, and it doesn't really matter the scale that you use on the x-axis because, again, the more you zoom in, the more it oscillates. But what you should notice when you sketch the curve is that, on the left-hand side of the y-axis, the tail end of our graph over here is living below the x-axis, and then it just starts going like that, kind of crazy, but it ends up underneath the x-axis. And on the right-hand side, you have the opposite thing going on. It's going like this, and it's ending up here. So as x is approaching 0 on the left, and as x is approaching 0 on the right, it's not settling on a value. Let's write that down. The graph oscillates between negative 1 and positive 1 on the y-axis, never settling on a value. Okay, so in this case, the left-hand limit does not equal the right-hand limit. And if the left-hand limit doesn't equal the right-hand limit, then the answer to our problem is the limit does not exist. So be careful when you're using your graphing device. Make sure that the information that it gives you is something that you're able to understand and interpret. Based on the table, it looked like the limit was 0, but yet I was really questioning that when every single x value gave us a value of 0 as we got closer and closer to 0. That seemed a little fishy to me. And then we looked at the graph and we zoomed in on the graph and we saw how those oscillations were just going crazy as we got closer and closer to 0. So be very careful when you use your calculator as a tool to help you in limits. It's a great tool, as long as you know how to interpret the information that it gives you.